Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at groups. So in mathematics, a group is a special type of set. So that set satisfies these axioms. So when you have a set that forms a group, it'll be a group under an operation, usually addition and or multiplication. So I've just called this operation this circle here. So for the set to be a group, it needs to satisfy closure, associativity, and inverses. So closure we've seen before. That means if you perform the operation on any two members of the set, you get another member of the set. Associativity basically means if you perform this operation on a string of elements, you can put the brackets wherever you like. We also need to have inverses as part of the set. So that means if G is a member of the set, so too its inverse is part of the set. I've used the notation G to the power of -1 to denote the inverse, but I may not be talking about the multiplicative inverse. It depends what the operation is. If the set forms a group under addition, then this would be the additive inverse. So this is just saying for every member of the set, its inverse, whether that be multiplicative or additive, also needs to be part of the set. So just note, because of axioms 1 and 3, it must also be true that the identity is part of the set G. So I've just called it I. Again, what the identity is depends on the operation. So if we're talking addition, 0 must be part of the group. And if we're talking multiplication, 1 must be part of the group. Why is that? Because we know that G and G inverse will be a part of the group. And if you operate on them, add them or multiply them, you get the identity. So that's why the identity needs to be part of the group. I didn't include it as a separate axiom because it follows from 1 and 3. So note that when you have a set that forms a group, the operation, be it addition or multiplication, doesn't necessarily need to be commutative. If it is commutative, we call the group abelian. And just note, a subgroup is a subset of a group that is itself a group. So when you're looking for a subgroup, a subset of a group, you don't need to check associativity or commutativity. That'll follow from the group itself. You only need to check closure and the existence of inverses. All right, this probably doesn't make a lot of sense, so let's look at an example. Let's look at Z4, the set of integers modulo 4. So to help us determine whether or not this forms a group, I've set up an addition table. So what we can see is that under addition, the integers modulo 4 are closed, because if you add together any two members of this set, you get another member of the set. So it satisfies the closure. Now, associativity is a bit harder to prove and would take longer. It turns out that for Z4, integers modulo 4 are associative. This follows from the real numbers, even though Z4 is not technically a subset of the integers or the real numbers. Remember that we can add numbers first and then reduce modulo 4. So that's just a short explanation as to why associativity holds. So let's look at inverses. So when we're talking about addition, we're wondering if the additive inverse of each element is also part of the set. And we see clearly it is. 0 is its own additive inverse, 1 and 3 are additive inverses, and 2 is its own additive inverse. So in other words, the additive inverses exist in this group because for any element in the group, you always have an element you can add to it to get to 0. So indeed, Z4 forms a group under addition. It is also commutative, we know that. So Z4 actually forms an abelian group under addition. What about multiplication? So I've drawn up a multiplication table of the integers modulo 4. So they are closed under multiplication. So this is satisfied for multiplication. They're also associative, but they don't have inverses for each element. In particular, 2 has no inverse. There is no number that you can multiply 2 by to get back to the multiplicative identity of 1. Similarly, 0 doesn't have a multiplicative inverse. So because we don't have inverses in the set, because there are times we have an element in Z4 but not its inverse, we say that the third axiom here has failed, and it turns out integers modulo 4 do not form a group under multiplication, but they do form a group under addition. Now, it turns out that there are some subgroups here. So a subgroup under addition is the set 0 and 2 from modulo 4. So these two form a group. Now, when I'm determining whether or not they form a group, I don't need to check that they're associative or commutative, because I already know that any elements of this set are associative and commutative. So all I need to check is that they're closed and that inverses exist. Well, they're closed because 0 plus 0 is 0, 0 plus 2 is 2, 2 plus 2 is 0. If you add together any of these two numbers, as we see up here, you will get just those numbers. It's impossible to add together either of these numbers and get something outside this set. So they are closed. And they are their own additive inverses. 0 plus 0 is 0 in mod 4. 2 plus 2 equals 0, or is equivalent to 0 in mod 4. So that's why this forms a subgroup. It turns out that for any group, there's a subgroup known as the trivial subgroup, because it is pretty much trivial. So it turns out the set containing only the multiplicative identity is a subgroup under multiplication, and the set containing the additive identity is a subgroup under addition. So this actually forms a subgroup under multiplication. So the reason is 1 is its own inverse, and 1 times 1 is 1. This is closed, and it has an inverse, the existence of inverses. And we already knew that multiplication was associative and commutative. So this is an abelian subgroup under multiplication. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.